Hello, thanks for listening in. It's great to have you with us. The vacuum gauge is defined by the covariant vacuum gauge condition. Any set of potentials satisfying this first order differential equation may be referred to as vacuum gauge potentials. The most important set of vacuum gauge potentials for the classical electron are the null potentials, where R nu is the vector from the retarded position of the charge to the present time field point, and it's easy to verify the velocity portion of the field strength tensor, F mu nu, for constant velocity motion. We can demonstrate the construction of vacuum gauge potentials on a space-time diagram. Here, the red arrow shows an electron moving with velocity beta nu. The Leonard-Weichert potentials for the moving particle A nu sub t are represented by the black arrow at a point in the space-time diagram. Next, we introduce the gauge field phi is equal to minus E log rho. A gradient operation on this field produces the space-like vacuum gauge potentials A nu sub s. And this space-like field is shown by the new arrow in the space-time diagram. The sum of the time-like Leonard-Weichert potentials and the space-like vacuum gauge potentials then determines a new set of potentials pointing along the light cone and orthogonal to it. These are the light-like vacuum gauge potentials. Now let's talk a little bit more about the vacuum gauge condition, which is really a first-order differential equation for the potentials. But it's not necessary to solve this equation to glean some very important properties. For example, it's possible to take the square root on the right side of the equation, giving two three-space vectors, and we note that one root is merely the complex conjugate of the other. Each of these roots can be applied equally to both electrons and positrons simply by changing the sign of the charge. The explicit form of the four divergence is not required to calculate the roots, but can be determined by simply evaluating the right side of the vacuum gauge condition, showing that the four divergence is equal to the electron charge divided by rho squared. Finally, we are showing the complex unit vector z hat, which arises naturally when taking the square root. This unit vector may be referred to as a polarization vector for the particle velocity fields and has a magnitude equal to 1. This polarization vector is similar to complex circular polarization vectors in the theory of electromagnetic waves. Now, the norms of our vectors, capital Z and capital Z star, simply reproduce the vacuum gauge condition. But note that it's possible to include particle acceleration fields as part of the square root. This has no bearing on the vacuum gauge condition, as the norms of the vectors Z or Z star are both unchanged. A glaring issue with the vacuum gauge condition is the fact that covariance is lost when calculating the square root. We know this because the vectors z and z star are three vectors, but we can reestablish covariance by defining the vector z nu, which includes the vacuum gauge condition in the time component. In this equation, we have redefined the four divergence of the potentials as the letter eta for simplicity and convenience. Now we can write the complex vectors z nu and z nu star in terms of the polarization vector z hat and its complex conjugate. Although these are complex vectors, the norms are both 0. Clearly, the vacuum gauge is quite a bit more sophisticated than the Lorentz gauge. In fact, as a reminder, our goal is to use properties of the vacuum gauge condition previously discussed to derive the set of Dirac Spinors. To accomplish this, we work in the chiral representation of the Dirac algebra with scalar and vector components of the gamma matrices shown here. We are also interested in the spin operators sigma nu and bar sigma nu, and we note that all four gamma matrices can be represented by this single matrix gamma nu. For reference, the set of four Dirac Spinors and the chiral representation are given in the red box. We see that the two spinors U1 and U2 on top of the dashed line apply to electrons and satisfy the momentum space Dirac equation on the right. Likewise, the two spinors V1 and V2 under the dashed line apply to positrons and satisfy a separate momentum space Dirac equation also on the right. Now let's write down the three null vectors that we derived from our analysis of the vacuum gauge condition. These are the light-like null potentials on the left and the null 4-vector z nu and its complex conjugate on the right. Applying sigma bar nu and sigma nu defined earlier, we arrive at a set of 4 2x2 matrices. Next, let's combine the operators on the potentials into a 4x4 matrix. This matrix is equivalent to the set of 4 potentials eigenstates. Similarly, we can also combine operators on the fields into a 4x4 matrix, and once again write this matrix in terms of a set of field eigenstates. We are now in a position to use our state vectors to calculate Dirac Spinors. Begin by appropriately choosing one state vector from the potentials and one state vector from the fields. Then introduce the particle mass m and organize these vectors into the Dirac Spinor U1. Here, the notation -n in the eigenstates indicates that all elements of the given column vector containing components of n are to be replaced with the components of -n. We have calculated one eigenstate, but not surprisingly, astute choices of the remaining state vectors can also be combined to produce the remaining 3 Dirac Spinors. This completes our stated goal to derive Dirac Spinors in the chiral representation. A more rigorous derivation might also include the traveling wave properties of Dirac Spinors. To summarize, first, vacuum gauge potentials have extraordinary powers well beyond potentials that are derived from the Lorentz gauge condition. Second, the application of gamma matrices to the fields of the vacuum gauge electron, as was done here, is an effective procedure to quantize the particle. And finally, the theory of the vacuum gauge electron needs to be reviewed by professional physicists. Thanks for listening in. We hope you've enjoyed this short video and have a great day.